All right, so let's get started. So today we only do 1 hour because I have a presentation in Taipei this afternoon. So we need to finish around like 11 today. And tomorrow, like we invited a professor from US to give us a talk in AB 101. So like for guys, if you join online or in person, then you can get 2 points bonus on your final score. So that is the head-ups. Then today I only prepared 2 Q&A because there are a lot, but I don't think I have that much of time to go through all of them today. So probably next time, then we'll have more Q&A about the stakeholder and interrupts together. Oh, one more thing, as next week actually we'll have no class, so actually it will be in 2 weeks for our next lecture. Okay, so the first question, I think there's a lot of you are curious about, like, because as you know, last time we say when we were doing the context switch, there is a thing called flush TOB. But in current architecture, no matter you are using the Intel or RISC-V or any AMD, actually there's a thing called TOB PID tag. So or another name is about the address space identifiers, so ASID. So actually, this kind of ASID or TOB PID tag is about for each page table entry, it will have one tag to identify which process it is belonging to. So in this case, if each translation plus their PID, like it is not really necessary to do the flush every time, and it is also correct because like this function is supported from Linux kernel 2.6.73, so just like from around 2011. So the thing is, with this kind of enable on the CPU, you don't really need to do TOB flush every time, but there are still some special case you still need to do the TOB flush. So actually, this is also the reason why, remember in this slide, so this flow chart is from Linux kernel 4.4. So under this Linux kernel version, actually there has already ASID enabling for the CPU. But the reason why here still comes a plus TOB function block here is because actually there are a couple more, but I only did 2. I think it is quite important and it's easier to understand. The first one is page table changes. So what do I mean for page table changes is, for example, your virtual to physical address, your physical address changes. So at that time, you need to update your page table. And because TOB tag is only to identify which process you are belonging to. So it doesn't really have a response to the update on the page table. So you can think about for process 1, it has a virtual address, maybe let's say like number 0, and it maps to the physical address number like 1, something like that. But when you change the physical address to number like 2 or 3, actually the TOB tag cannot help on this. So in this scenario, you still need to flush the TOB. So the timing for the page table changes actually it happens a lot of times, but copy on write is I think it's the most general thing you can easier to image, because when we're doing the copy on write, we need to update to the new physical address, right? When you are going to write a page, then we are going to do the copy to the other page, so you need to the process page table should be updated. So this is the first case. And the second case is a more system stuff, because when we are saying we are using something like tag stuff, actually tag usually is a 8-bit or 16-bit string, right? And for example, if you're using an 8-bit string, then it means like you can have at most 256 tags, right? From add 0 to add 1. So you have 2 to the add, you have 256 possible tags there. So it also means you can only identify at most 256 process. So when in your system, your total number of process is more than 256, then you need to do the ASID reuse. So ASID reuse is you need to reassign the ASID, and because the ASID changes, so you need to do the TOB flush. So Here are two very, I think, common cases that kernel needs to run a flush TOB. So in addition to these two scenarios, like if there's nothing changes on the hash table, then kernel will not do a TOB flush during the context switch. Okay, so this is more about the TOB flush stuff. So there's another question is about how to avoid CFS triggering rescheduling frequently. Because there is a scenario as if all the process in the system has the same nice value or has the same priority, then according to last week, what we talked about is like we need to reschedule the process if some virtual runtime is more it's more than others. Okay. The thing is, actually, in Linux, there is a thing called wake-up granularity threshold. So this threshold is a global kernel parameter. So before preempting the process, because maybe if we have two processes, P1 and P2, and for example, P1 starts to run first, and then after some microsecond, P1's virtual runtime might be larger than P2 because they have the same nice value. So if there's no this policy, then there's a possibility that P2 will preempt P1, and P2 will start to run in a very short time, and then its virtual runtime will become again larger than P1. Then P1 will preempt P2. So P1 and P2 will preempt itself in a ping-pong way. So to avoid this, there's a wake-up granularity threshold. So it looks like kernel will first check about the two virtual runtime gap, the difference between two virtual runtime. So if the difference between two virtual runtime is larger than this threshold, then kernel will do the preemption. Otherwise, will not. So the global kernel parameter for this one usually is a default parameter. So when you put up your Linux kernel, usually the number is like around 100 microseconds to 1 millisecond. It depends. In most cases, it will be 1 millisecond. But if you are going to make it have a better fairness, then you can, if you are system administrator, you can set it to 100 microseconds. But all the process will share this number. Okay, so that is another things for CFS. Okay, so let me quickly go through some things, the recap last time. So process context switch, first we need to talk about process context, and you can think about process context is just like an environment the process is using to run. So including the user address space, like the hash table stuff, and then the hardware register. So all of the register you learn from your computer organization, it needs to run the process, then that needs to be stored in, for example, the PCB or the text structure. So program counter, all those kind of register stuff, we need to store the stack pointer, those kind of stuff. And also because for each user process, actually, it is possible to switch to a kernel mode, right? So there is also kernel data structure related to the user process. So those all together, they are all belonging to the process context. So when you are going to switch your process context, then you need to switch those kind of stuff. Okay. So process context switch, usually there are two main components. The first is to switch the virtual memory mapping. So the main part is the patch table. So because we are going to switch from one process to another process, so we need to switch a patch table. So you can think about if you are going to switch from one process to its own thread, then it still needs to run a switch-mm because kernel cannot, at that time, kernel cannot identify you are switching the process or thread. But when kernel starts to run the flow, and then kernel will find actually you are going to switch from a process to a thread. So actually the switch-mm will not do anything, or sorry, will not do too much of things because there are still some registers they need to maintain. Okay, so that is for switch-mm. And switch 2, actually, it is about the state switching. So including the process register, architecture specific set, and so on. So here are all like possible things it needs to do. Okay. But yeah, that's just a lot of details. So if you're interested, you can go to check about it. But again, this any of them will not be on your exam to ask you about what is that about. And if I remember correctly, there's a question is about like there is a preprocessor data area. So for this PDA, this is belonging to the user process. Actually, most of the things here they are belonging to the user process, not the kernel. Okay, there are only very few. For example, update review set. This is quite related to the kernel, but most of the stuff those are for user process. Okay. Okay. So one important thing is actually in the systems, there are a lot of switching stuff. So actually there's CPU mode switching from when there's a process and it's a help from the hardware and it submits the system code, then there is a switch from kernel mode to user mode. So this is a CPU mode switching. And there is also process context switch to switch the process like from one CPU out and then to switch in another process. Okay. So before switching to kernel mode, CPU should set user mode context. So actually this part is very similar to process level context switch. Or I should say, actually, process level context switch and CPU mode switching, actually they are very similar idea. They have the same concept. The difference is how much of information the system, the CPU needs to set back to the memory. For example, if we are doing the CPU mode switching, actually we don't really need to do, for example, you don't really need to do the hash table setting, right? Because the user mode and kernel mode there, it doesn't really change the hash table. So you don't really need to do the switch MM stuff. And even for switch 2, most of the stuff you don't really need to change because your kernel is the same. And the only thing you are going to set is some user level register because you are going to switch back to the user process after finishing the kernel stuff. Okay. So here are the things like you need to set for user mode, for example, the program counter, because you need to know where is the point you call the system code. So after handling system code, you need to return back this program counter. So usually program counter you can think about a specific like a physical address in the systems like that. Okay. So when we say set context, we generally mean to write back all those registers to the corresponding process descriptor or the text structure in the main memory. Okay, so let me use this quick example to finish the recap. So this is how to run system code. Oh, before running the system code, actually the reason why we need system code is for the user process, for most of the user process or for all the user process, actually they device. So when they are going to access the hardware device, they need the help from operating system. So system code is a bridge to bridge the user process and the hardware resource. Okay. So when, for example, when the user process needs to print something on the screen or when it needs to write something in the disk, those are all the functions that will touch the hardware device. So they all need to run the system code to handle this kind of request. So how to run system code? User space applications must somehow signal to the kernel. And the kernel will run the system code handler to handle the things that the process needs to help. Okay. So here's a detail. Actually, system call and interrupt is a very similar idea. I will show you how interrupt works later. And then you can think about system call is a special case for interrupt. It's just like the software interrupt in the case. So it's more like this. It runs a thing called interrupt 0x80. So 0x80 is a very special special interrupt instructions that the interrupt to, you can think about, actually for each interrupt, they have their own number. And maybe interrupt 0 usually is like the timer interrupt, and interrupt 1 is maybe the read or disk interrupt like that. So most of the interrupt they are related to the hardware, but we need some way to virtualize, to mimic how this interrupt works. So people or like Linux guys, they think about maybe we can have this kind of virtual number to simulate the interrupt stuff. So in this case, the software interrupt counts, or software interrupt, people call them the system call. Okay, so this one actually, I would say like the hardware part for doing this system call or interrupt, actually it is very similar to the interrupt handler. Okay, so we will have more details about the interrupt later. So coming back to our poll example, if each process is a submarine, so for process A, if it is now in the user mode, then it is above the surface. So when one day it needs the help from kernel, then it needs to dive into the water. So same again, because no matter the process or the submarine is above the surface or dive into the water, actually this is the same submarine. So it means no matter the process is running in the user mode or the kernel mode, it is still on that CPU. Okay, you can think about submarine just like a CPU or like the CPU plus that process. Okay, so when there is an interrupt, just like interrupt like let's interrupt your x80, and you will store the system call number to the register. So the CPU will switch from the user mode to the kernel mode. Okay, so now the CPU can start to run the system call handler. And this EAX is going to let the CPU know which like system call handler the CPU should run, because there are, if you go to start your assignment, actually, if you open Linux, there is like 500 something like system calls there. So for among this 500 system calls, they all have their own function. So for example, like if you are going to write something, then probably you're going to use a system call number. I'm not quite sure, just like 1, for example. So this system call number 1 will be put into the CPU register. So CPU can read this register to know, oh, actually you are not calling which system call. There's a mapping between them. So after this system call number, they can be translated by this kind of system call table in the kernel. So this table will point to the main function, like which function you are going to run, like that. Okay. So after getting after the CPU be redirected to the function, CPU can read out the kernel function and then to handle the system call requested by the user. Okay, so after system call handling, actually the submarine will go back to the user mode. And you can think about, after handling the system call, the CPU will switch back to the user mode, and then the CPU will switch back to run the original process. So this is also the thing like why we need to do the mode switching, because at this step, actually you can think about CPU is now running kernel related like data structure or the kernel related data address space, like the memory, physical memory place. So we need an information to know which accurate address as the user process, like last time it stops. So you can think about this. For example, this one is some physical address, and then the CPU will read out the PCB, and then to know, oh, actually the user process is now in which physical address. So when this physical address is pushed into the CPU, the program counter, for example, then CPU can switch back to the user process. So it is all about the program counter switching, because at this step, program counter is in some physical address, and then after switching the program counter to this address, then CPU can move back to running the user process. Okay, so this is the case of how system call handler works like. Okay, interrupts. Interrupts is a very important stuff, because interrupt can let the CPU interact with the peripheral devices. Okay, so how CPUs work with slower hardware device? So there are two very typical ways. The first is called polling. Polling is to periodically kernel checks hardware status and response accordingly. Okay, and the other is called interrupt, just like let the hardware to signal to the kernel. So polling, you can think about the CPU will wait there, busy waiting there to wait for the kernel to check about the hardware status. And the hardware status, you can think about actually no matter what kind of device, including your keyboard, your mouse, your disk, your SSD, no matter what kind of like this kind of peripheral device, actually there is a register on it, and there inside the register it is about the status if the request is ready or not. So kernel will keep asking about the device controller to check about, please help me to check that hardware status. If the status becomes clear, becomes okay to run. So this is called pooling. Interrupt is about device controller will directly tell the CPU to issue the signal to the CPU to let the CPU know actually the request is finished. Okay, so what causes interrupts? Okay, so our device physically produce electronic signals and which are directly into input pins on an interrupt controller. So I think this is quite hard to understand. So I draw a very toy example here. So imagine this is your motherboard, and on your motherboard, actually there are CPU chips, and there are things called north bridge and south bridge. Okay, so north bridge usually is for the memory controller hub, and south bridge is usually for the I/O controller hub. And the reason why north bridge it looks like closer to the CPU, and the location for south bridge it looks as a little bit far from CPU, and that is reasonable because north bridge is going to use for handling memory. So memory is faster than storage device. So if now memory device is if they change their position, if north bridge is here, then the memory signal should work for a longer wave. So the latency will become higher. On the other hand, because south bridge usually is handling peripheral device, so the latency is 10 times or even like 2 orders slower than memory. So it doesn't really matter if it is a little bit a little bit far to the CPU. Okay, so both north bridge and south bridge together, they are called chipset. So you can take a deeper look as usually like DRAM and GPU, they are controlled by the north bridge, and then for the keyboard, hard disk drive, PCI, SSD, they're usually controlled by the I/O control hub or south bridge. Okay, so interrupt, it works like there's a thing called interrupt controller inside a south bridge, or like in current system, there's a thing called I/O APIC, but I mean they're the same things. So you can think about they're just like an interrupt controller, and no matter your keyboard, your hard disk drive, your PCI SSD can send a signal to the interrupt controller. So the controller will tell the CPU to do the interrupt like this. So when you type the keyboard, no matter what kind of character you are typing, then there is a signal. There is a signal will signal to the controller. Then controller will send this. You can think about like it's just like package stuff in the networking. It will send those kind of package stuff to including the content for the thing you type, and then the information the CPU needs to resolve, like send into a local APIC inside the CPU, and CPU can resolve the information, and then CPU can start to run. Like there is a kernel function to handle it. So this is the hardware part. And then one thing to let you know is actually after 2019, all north bridge functions have been integrated into the CPU. So in most of the recent CPU, especially for x86, there is a memory controller inside the CPU. Okay, so usually there's no north bridge now. DRAM and CPU, DRAM and GPU, they were directly connected to the CPU. I mean, CPU's memory controller. Okay, so just a very little stuff to let you know. Okay, so there is another way to cause interrupts. I mean, this is the hardware way to cause the interrupt. And the special case is people call them software interrupts or exceptions. So exceptions are produced by the processor while executing instruction either in response to a program error or abnormal condition. So programming error including divided by 0. So you can think about as how CPU interrupt itself, right? Because programming error is CPU run one instruction, and CPU find actually the instruction is not correct. So CPU will interrupt itself to let the kernel to take care of this kind of stuff. And there is also another thing is called abnormal condition. So just like patch fault or system call. So system call, because it is issued by the CPU. So you can think about it's just like CPU interrupt itself. Okay, so the difference between interrupt and exception, actually there's a lot of definition, but here, the definition as exception is more about CPU to interrupt itself, and interrupt, the hardware interrupts is the peripheral devices, they interrupt the CPU. Okay, so that is the way I think like you can differentiate these two stuff. But I mean, there are a lot of quite more definitions on different textbooks. So yeah. Okay, so before talking about interrupts, we need to talk about the thing called interrupt request, or you can see IRQ in a lot of places, like a lot of spec that have IRQ. So different devices can be associated with different interrupts by means of a unique interrupt value. So this one, unique interrupt value, you can think about the system code number. Their concept is very similar because once again, system code is a special case from interrupt. So system code's implementation is very similar to interrupts implementation. Okay. So you can think about keyboard when you attach your keyboard to the computer, then keyboard will get at least one interrupt value. So the mouse, you can get another interrupt value. The SSD, your hard disk drive, the SD card, you can get interrupt value for each of them. Okay. And there are some things called interrupt request. It's a specific request associated with a specific device, and the kernel know less. IRQ is about because when you register your peripheral device to the CPU, then the next thing is when you submit the signal to the CPU, how CPU knows this signal is from keyboard, that signal is from mouse. So together, this interrupt value and interrupt request together, you can think about it as a system code table and their system code number like this. So IRQ 0 usually means the timer interrupt. IRQ 1 usually means keyboard interrupt. And then because as we mentioned, there is only 256, there's only, I think it's 8 bits. Usually in the ancient system, there's only 8 bits of the tag. But the thing is, there is a dynamically allocated IRQ number for a PCI device. So this is also like basically more advanced stuff because nowadays there are way more devices attached to the CPU. So in ancient time, we only need 8 bits, but it is not easy to extend to like 16 bits or 32 bits, those kind of stuff, because it increases the power cost. So one trade-off or like one workaround is to use the dynamical allocation. So CPU will take care of this kind of stuff. Or I should put it like this. The controller inside the CPU, so like this. The controller inside the CPU called local APIC will take care of this kind of dynamically allocation stuff. So after having this kind of APIC things, your interrupt numbers can be more than 256 because there's some mapping between them. Okay. So this one just want to let you know what when you open your like hardware spec, what the interrupt will look like. So here are like 256 numbers here because from 0x00 to 0xFF, right? So this is a default processor interrupt vector table. So here are all interrupt they have here, and during the boot, during your system boot, like some interrupt will be inserted to this interrupt vector table. So you can see like after booting, there's remaped by BIOS. So there's new interrupt will be inserted from here 0x08 to 0x0F. Then here comes IRQ 0 is system timer, IRQ 1 is keyboard, and cassette, serial, sound card, floppy disk, power port, and then those will be mapped to this vector number. So 0x0H will become the IRQ 0. Okay, and there is also some others, for example, IRQ add to 15. Okay. Okay, so here comes the things called like software interrupts. So here after 0x80, there's a software interrupts here. Okay, so once again, because when you start your operating system, there is also some software interrupts like here. So actually, we will have another thing called operating system will remap this table again. Like the remapping, you can think about just like operating system will include some more interrupts into the interrupt table, so they need to switch the interrupt number and the hierarchies mapping relationship there. Okay, so this is just for x86 interrupt vector table. So I mean, if you are not using like RISC-V or AMD, something like, or ARM, sorry, or ARM, actually you will have different interrupt table. Okay, but again, this one I think is not super important. I mean, just know, hey, actually there is a mapping between like timer interrupt and there is a specific IRQ for the timer interrupt, just like a system code. I mean, system code number, like for example, if I remember correctly, 1 is for read, 2 is for write, like that kind of stuff. Okay. So what is important? Interrupt, how interrupt works is important. How an interrupt works. So the right-hand side is the software, sorry, it's a motherboard, and then we keep the salt bridge, and then we remove the nose bridge. So we include the memory inside. So you can, in this example, you can see where the interrupt controller is not connected to like at different device. So there's a timer, there's a keyboard, and probably there's a maybe mouse, for example. So this one, IRQ0, IRQ1, you can also think about it's just like the wire to connect to the device. So different wire means different interrupt vector numbers. Okay, so IRQ0, this is a real wire to connect with the timer. And then there is a wire connected to the keyboard. You can think of it like that. Okay, so first, power device send out an interrupt signal. So if you look at the keyboard, then when you type something on the keyboard, then there's a signal sent from keyboard's controller to the interrupt controller. Oh, one interesting thing is actually no matter you're using a keyboard or mouse, actually there is very tiny controller on the keyboard or mouse. So including your disk, your SSD, no matter what kind of peripheral device, nowadays there is very tiny controller inside to do the control. So this IRQ1 is submitted by the controller inside the keyboard. When you type some things, then there is a electronic signal will be sent to the interrupt controller. Okay, so once the interrupt controller receives IRQ1, for example, the CPU stops current executions. So interrupt controller will send to stop the CPU, for example. Okay. Then the thing is, inside the interrupt controller, there is an interrupt vector table. So it is going to do the translation. The translation is more like this. When you get like IRQ1, then how to do the translation to the interrupt vector number. Okay, because the interrupt vector number, then IRQ is a stuff like kernel cannot understand, but this vector number is what kernel can understand. Okay. So when the IRQ1 is sent to the interrupt controller, and interrupt controller will do the translation to translate IRQ1 to, for example, IRT0x81. Sorry, this is just an example. I mean, it doesn't really depend on any architecture real stuff. I just give you a very quick example. For example, if the IRQ1 is translated to interrupt number 0x81, then the controller will send the 0x81 to the CPU. Okay. So the stop is after you type something on keyboard, what you are going to expect is the kernel can handle your request and then to do some actions on your keyboard typing, right? So the thing what we are looking for is how to find the kernel function. I mean, this is IRQ1 and this is interrupt vector 0x81, but so there is a kernel function. I mean, what is the kernel function that can handle the keyboard, and what is the location in the memory? Okay, so this is what our next step. So after the CPU received the 0x81, then, sorry, let me check. Okay, then CPU will do a very simple calculation, because 0x81 means you are the 81's interrupt vector. So CPU will time by 4, and then it will be recalculate to 0x204. So what is 0x204? Actually, if you still remember, we have in a hardware aspect, we have address for the interrupt, and there are total 256 interrupt vectors, right? So for each interrupt vectors, we can link to each interrupt function. So because there are only 256 interrupt vectors here, so the first interrupt vector it will be stored on a best locations here. So if we assume the best address is 0x0 now, then 0x4 will be ISR1, interrupt service routine 1. Okay, and then 0xF will be ISR2. So ISR81, the 81 interrupt service routine will be located on 0x204. Okay, so this is locations for the starting vectors. Okay, but I mean, in the real system, this will not be 0x0. So you can just think about there is a shift, there is an offset here. For example, they start from a specific offset, then all of the rest of the 255 vectors will be shipped by the offset. Okay, so another question is why is 4? What is like, what is timing 4 here? And we need to point out one thing is we need to know where is the starting point for each of the function. So when we are going to say we are going to handle the keyboard for the IRQ1, what we are looking for is a starting point of the function. So maybe the function is stored in some place. We need to find the starting point. So the starting point is the code segment plus the instruction pointer, right? So this is the 32 bits. And if you check the CPU architecture, you can know the starting point is start from the code segment and instruction pointer. Or if you think it is too complex, you can think about this CS plus IP. It is a little bit like the program counter. We are finding about the program counter. Where is the starting point for the function? Okay. And the reason is byte, not bit, is because memory we are using a byte addressable address now. So the address mapping in current DRAM is using a byte. So the smallest granularity should be 1 byte. Okay, so here we use 4 bytes, so 32 bits to represent the CS plus IP. Okay, so after locating where is the vector for ISR81, we will read out the CS and IP. Okay, so the CS and IP stub will point to the starting address of the function. So like this. For example, this is the function bodies for the interrupt service routine 81. So you can see like the first line of the maybe is, for example, what is the data in IRQ1, what is the keyboard, and there is a lot of instruction here. So we need to know where is the first instruction, what is the location for the first instruction, and CS plus IP stored in this vector can help us to locate where is the starting point. So when CPU read out this this address, CPU will resolve the instruction, and CPU will know, oh, okay, so this is a CS plus IP location. Then CPU will switch the program counter to this location. Then CPU can start to execute the ISR81. So the interrupt service routine 81 is to handle this keyboard like interrupt stuff. So this is how CPU get the interrupt and how CPU can know where is the function. Okay, so if you now have another, for example, ISR82, for example, 82, for example, is for IRQ2, and ISR82 might be someplace in the memory. Okay, and because ISR81 and ISR82 or ISR something will not be in the same size, because ISR81 is the function body. So probably if this ISR body, for example, is like 100 lines of code, and maybe ISR82 is maybe 1,000 lines of code. So the size of ISR81 and the rest of the ISR usually will not be in the same size. So it is not possible to first get the location about where is location for this. So this is the reason why we need this vector at the very beginning, because this is the fixed location. So we can do the calculation, we can know which vector it is, and we can get the starting point of the function. Okay, so because there, I think you have a problem is why not just directly get the starting point of ISR 81 or ISR 82, right? And the reason is because this the size of ISR 81, ISR 82, or ISR something is not it's not fixed, because like it depends on different kernel versions and different. For example, when you are going to implement your own interrupt service routine, then there will be another maybe ISR like 254, and the size will not be the same as ISR 81. So it is hard to know in advance where is the location for those ISR. So we need some help, we need some assist from a simple data structure. You can think about this data structure is to quickly identify, to quickly locate where is the first address of each of the interrupt service routine. Okay, so that is the case. Okay, question for this one. Okay. Do you need me to repeat again about the list flow, or it is okay for you to understand? Okay, so maybe let me go through it once again to show this step again, because I mean we only have 5 minutes, so let me do it again. Okay. Okay, so now our problem is you type something on the keyboard. So maybe you type a sentence on the keyboard, and the keyboard controller sends the sentence to the interrupt controller. So your kernel is waiting for your information and then to show your information on the screen. But how can kernel know you are now typing your keyboard, and what should the kernel do for this kind of kernel keyboard interrupt? So this is what we are looking for. Then when you type the keyboard, actually the keyboard is connected to the interrupt controller. Oh, this is the motherboard. So on the motherboard, there's an interrupt controller connect with the keyboard with a real wire. So there's a wire. So when you type something, the wire, there's a signal to send on the wire, and the interrupt controller receives the signals. It will be identified as IRQ1. No matter what kind of signal sent by the keyboard, it is called IRQ1. Okay, so if you have another timer, then send a signal to the interrupt. The interrupt controller will check which wire it is. If it is the first wire, then it will be IRQ0. So it depends on which wire it is. So when interrupt controller get the IRQ1, like the second wire, then interrupt controller will do the translation for the IRQ1 to the interrupt vectors. Okay. So this translation is because IRQ1 is not recognized by kernel. Because if you look at this table, actually this table is remapped by the BIOS, and the kernel will remap it again. So kernel doesn't really know what is IRQ1 or IRQ0. When the only things that people all can share between them is the interrupt vector number, and then you need to check for the interrupt vector table. Okay. So doing the translation, IRQ1 can be translated to the interrupt vector 0x81. And 0x81 will be sent into the CPU. Okay, so our next step is, so where is the starting point for the interrupt service routine? Interrupt service routine is a function that is going to handle the keyboard interrupt. So for example, the function is maybe like there is 100 or 200 lines of code, and it will specify to say the first line of code is going to check the keyboard status and then getting the keyboard like stuff of that. Okay, so you can think about ISR is just a part of the code. Okay, so when you have this kind of interrupt vector number, the CPU will time by 4. So 4 means 4 bytes. Okay, so this timing by 4 is going to help to locate where is the vector for the ISR 81. Okay, so the reason to time by 4 is because what we need to get is the starting point for each ISR. So the starting point is an address. So you can use the code statement plus instruction pointer, then you can get the address. And the code statement plus instruction pointer is 32 bits. So here is 4 bytes. Okay, so all of the interrupts, they will be mapped to one interrupt service routine. And the vector is going to redirect the CPU to know where is the starting point for each of the interrupt service routine. Okay, so after doing the calculation, CPU will directly get the data from this memory address. Let's say 0x204. Then CPU will parse the information, and CPU can know actually there is a CS plum and IP plum. So CS plum and IP plum, CPU will translate to the memory address. So CPU will once again access the memory by using this CS plum and IP plum. And this CS plum and IP plum will point to the starting address for the interrupt service routine. So because this is from 81, so this CS IP will point to the starting point for interrupt service routine 81. Okay, and those are all kind of a bunch of code. And what we are going to know is the starting point, because after knowing the starting point, CPU can do the automatic work to get the second instruction, the third instruction, and the fourth instruction, and so on. So what we are going to know is just the starting point. So after getting the starting point, CPU will start to execute the interrupt service routine 81 by move forward one by one for the instruction. Okay, so this is how CPU handle the interrupts. All right, so that is the case. So I think that's for today. And then next time we'll talk about the memory management stuff. Okay, thank you guys.
用这个论文也他们的 work time 来会是，我问他们说，那他哪一种工作要看是不是 time critical 的，是比较好是。
这个应该还没有教到，这是下一次要教的。然后你如果说要问哪一个是 time critical 的话，就是假设你今天从网卡读了资料回来之后，你要先确定这个网卡的封包的格式是正确的，这样还不会影响到就是重送这件事情。那你确定完之后，你接下来就是要把资料从网卡的封包，就是搬到例如你的电脑里面的记忆体。可这个搬动就不是这么重要，因为你顶多就重送而已。对，所以它就从一个 work 来讲，就是从一个 task 来讲，它就会分成有重要部分，通常就是确认这些资讯的正确性，metadata 的正确性，然后有不重要，也没有到不重要，就是可以被推演的部分，就是的一些资料搬移的部分。对，这个大概就是 interrupt handler 的区分这样子。对
OK， 好。
但这个下一个礼拜才会讲，因为这个目前还没讲到这个。
好 ，OK， 对了，然后我之前就是上一次吧，我好像有问那个助教，就是有问助教说，就是你装不装，但他好像还没有回我，就是不知道他有没有收到这样子。
有因为他们基本上应该不会回，因为毕竟记得人很多，所以应该是最后我们会把大家的问题就是把它拿到展现到分数上面去，然后让你们在最后再来 check。所以这个就只是做个就是有点像记录，说你有记这封信，然后最后如果你看那个分数没有被加上去，说这样这封信的数要拿分就可以了。
OK， 啊，最多就是加6分。
对，就是加6分。
好 ，OK， 所以 OK， 所以最后到会有 Excel 表统计，然后大家会自己确认，然后如果说最后真的有少加，就是再用这个计。
没错，没错，没错。先，
我这边会不太懂，
因
为我听不太懂。
你说整个吗？
就是有点细节，就是比如说，它这个转换是因为 CPU 看不懂这个 IR 多，
是因为 kernel 看不懂 IRQ， 因为你这个地方是要去就是让CPU 可以找到对应的 interrupt vector table， 这样。然后因为 IRQ 它是有点像是怎么讲呢？ IRQ 它其实不是在 interrupt，因为 interrupt 是这里，就是侧边这边，IRQ 只是其中一部分的 interrupt 而已，因为还有别的，就是它这边还有系统本身自己的 interrupt。IRQ 只是周边装置的这些 interrupt，然后刚才提到说，像 CPU 还会自己去 interrupt 自己，所以像那 page fault 在这个地方，但 page fault 就不属于就是外部装置的 interrupt，
最后不装置是 IRQ。
对，外部装置 IRQ，
哦，
对，所以它这个地方就是会有各种，还有自己就是 always 可以自己再定义这些特殊的 interrupt，所以它变成是它会有很多种各种 interrupt，但是呢，这些有没有 interrupt，它都会被集结在一个 table 里面去做对应，这样子。
可是这个不是说科老知道他们对应关系吗？
我看一下哦，
还是只是科老知道怎么转换？
诶，对，就是这个其实是 kernel 有那样 table 可以做转换，就是 CPU 里面有那样 table 让 kernel 去做转换。
哦，
对，
那这个 CS 跟 IP
就是比较像是call segment instruction pointer，比较像是你可以讲就 program counter 啊，就是 C 加 IP 是 program counter，它就指到下一个要去执行的地方，这样子。对，
所以就是那个 vector table，
这个是 vector table，但这个 vector table 是要去指到
这个 service routine 嘛？
对设备主线的开头。
哦，
就是它这个是辅助的资料结构。就是今天如果我假设你的设备主线都写一样长的话，一样长的扣，你就不需要这个了。对，因为这个里面就只存这个设备主线的首位置而已。这样，
就是看它从哪里开始跑。
对，就看它是在放在什么地方。
哦，好，那为什么这个0x81乘44这个会变大？
0x81，我要，我写错了，234才对。32，081，324，
324
对，324才对。
哦，
我写错了，我再改一下。
好
好，sorry。
不要紧。就是怎么样说要脱离的那个软件。
嗯，
那这样
等我一下哦。
好。
就是动作很慢。
好，那
这两种是就是它是折翼吗？还是立方？
你是说对于 CPU 来讲吗？
对，
同时存在，它可以同时存在，
可以同时。
可以同时存在。
OK，好，
好，谢谢。
那我想问这个为什么就是乘以4去拿到它的系数？
哦，乘以4的原因是因为它这个就是大小就是400的，因为它里面要存这个 CS 加 IP，然后 CS 加 IP 个别是我们一说个是200的，所以它总共加起来这个是400的。对。
CS 是 call
segment 对，然后 IP 是 instruction pointer，然后有这两个，它就可以去就是定位到它要跑的方向在什么地方。
byte，所以是8bit。
8bit，对，8bit 没有，因为它这个应该是32，应该是可以的，应该是16bit，
哦
2 byte，
，byte 各2个 byte，
对，应该各2 byte。
所以跟刚讲那个什么有256个 interrupt vector 是无关的吗？
是无关的，
哦，好，
对，是无关的，因为它这个地方指出来是在这个 memory 空间上面去做定位，对，所以它不管有几个，它都是总共加起来就是400，它会影响到的就只有这边是0到25，还是0到500、514这种的，对，
了解，谢谢。
谢谢。
想问一下，就是我们在 keyboard interrupt 的时候，是每按一个按键，它就会去处理这样的一次？
理论上应该不会，就是它会有一个 buffer 去存你现在有的东西，然后它可能存到一个 buffer 满了之后，它就一直跟 CPU 说这样子。对，因为毕竟我们在打的时候，它其实送这个讯号应该只需要几秒就送到，所以它不需要每个都送到这么及时这样子。对，
谢谢。
所以可能 process 到底什么这个 process？
哦，有，我去查了，就是我看大家的说法是 kernel process 跟 kernel 对，它是 大家是可以混用的，所以
比较限量。
它严格来说我觉得啊，从我定义来讲，它应该是 kernel 对，它应该没有 kernel process。
就只有 kernel 对，为什么？
对，因为如果是一般 process 的定义的话，它是要有自己的 array space 的话，
然后自己这边的定义是 virtual address space，是指说要有自己的 user address space，不是指 kernel 嘛？
对，
所以基本上kernel process 就是 kernel 对的，但是 kernel 对的，所以他们根本不是那个 process。
对，就是基本上，我觉得如果要就是严格讲，它其实是 kernel 对，它没有 kernel process，但是因为大家会混用，对，所以大家会有 kernel process 这个，对，因为我去看了一下 ChatGPT，它其实也是给出很类似的答案。
对啊，我也是这样查的。
对，所以，但我觉得这就是名词上啊，因为毕竟这个东西已经被用很久了，所以大家会很容易去把它混用。
反正它就只是一个 script 的是在就是在背后执行，然后都在 kernel mode 执行的一个。
对，然后它没有 user address space 那个部分。
对 process 的定义就是它指这边的 virtual address space 就是指说主要就在讲这个 user address space。
就是通常我们会说 process 是它应该也有这个下面那个部分的。对，因为你上面那部分是所有人共用的，它本来就不是某个 process 单有的。因为这个上面这一块是所有人对，一切都一样空间去。对，
好，我想问一下，如果是查的话，这样子，我这样写应该没错吧？所以它是这样子，就是它是先硬体来的话，然后就是会有 I/O APIC 去做处理，然后做一个转换转成 IV 的那个 vector，然后传给 CPU 里面的这个 local APIC，
对，
然后 local APIC 用这个 IVN 去查这个，
没错，
这样是一个 table， 所以这个 table 有点像这个算是一个，这算 IVN， 就是算这边就是算那个 table 吧。
这个 table 我觉得它比较像是，就是你刚才讲那个转成那个 IBN 应该是
在这边，
在这里转完 IBN， 然后它这边
去查 table，
转过去之后，对，它会有一张 table 是去对应，但这个其实我觉得它也不算 table，它就是一个vector list， 然后它这个 list 主要就是让我们知道每一个 ISR 的起始会在什么地方。
就是这段吧 ，CSIP，
对，
从这边然后对到这个，就有点像是查，也算是像是查表，但它其实就只是一个 vector，指向一个它实际的位置。
对，
好，了解。
对，
好，谢谢老师。
我问一下这个，因为你不太懂这个，他说这个，你说做 CPU mouse switch 的时候，他会做 context switch，但它不是一般，它不是那个。
就是我觉得 context switch 的定义很 rough， 就是 context switch 其实就只要你有做资料的储存，就是储存回你的 PCB，它是需要 context switch。可是你要存多少资料这件事情是不一定的，因为你 CPU mode switch 的话，它有做 context switch， 它做 context switch 就是把 user 的，就是你的 program 他们现在只要拿去把它存下来，因为你没有做这步的话，你 kernel 做完是。
这个动态分配是什么东西？
对啊，端好。动态分配就是说，这其实没有讲到，就是 APIC 它其实是一个，就是可以用你的软体去写，你要去注册新的 interrupt， 因为你现在 interrupt 总共就只有256个嘛，所以你一定会用满。毕竟你只要超过256个，你就不能查了。但你现在的电脑
包括软体吗？
没有，256个是不包括软体的，就是硬体的。
原
本的8 bit 就是256个，对。然后它这边就是让你可以透过，它会把某些 IRQ reserve 起来作为特殊用途，然后它有点像是会用多个人去共用同一个 IRQ， 但是它会有一个子表格就去做一个转换，对。
所以这个是他在开机的时候才会去，
他在开他 always 可以管到这一块。对。
好，这样子。
嗯